Good morning, everybody. Yes, today last time we started a lecture and then my nose started bleeding and I was feeling horrible. I didn't get out of bed till Sunday afternoon. So I'm feeling a little bit better. So we're going to do 2.6. We didn't do that last time. Sorry about that. So here's 2.6, definite integrals and areas between curves. Because up until now, we use the integrals to find the area between some function and the x-axis. We find the area of that curve there. Now we're going to look at two functions. This is f of x and g of x between a and b. We want to know that area. All right. So there are two different methods of finding definite integrals. And we looked at some of the rules last time. So there are two methods of finding definite integrals by substitution. First is by finding the antiderivative of the function using substitution. Evaluating using the evaluation theorem we did last week. So finding, make that capital F. Finding the antiderivative of the function and then evaluate using the evaluation theorem. And then the other one extends the process of adding, but extending the process of substitution to the definite integrals by changing the limits of integration. So those are the two methods we're going to look at here. Whereas what we're looking at here is We're now going to change the limits of integration, the upper and lower bounds. So the first theorem we're going to look at for this chapter is the substitution theorem. Right. So, and actually here in the packet I gave you last week, we use this one here. Now write down so we could use it. So if G prime is continuous, on the closed interval AB, and the function f is continuous on the range of the function g of x, we'll call that u, then the theorem says this. The integral from a to b of function within a function, the composite function f of g of x, this is what we have, the f of u du, so we have that all taken care of. We can now convert this to the f of u du by defining g of x as u. So we have f of u, and then g prime of x is u prime, or du. That's what we have f of u du. But because we have the bounds of a to b that are all functions of the function g of x, so we're changing the bounds of integration with respect to the x, the second function. So as long as we have a composite function, this will work. And it's in the form f of u du. Let's look at example 1. Evaluate this function from -1 to 1, 3x squared, x cubed plus 1 dx. All right, so what we have to do here first is we got to look at our, does it match that condition? So inside here, we're going to call that our g of x. X cubed plus 1. We'll call that u. Then the g prime of x is 3x squared. We'll call that du. Du, since it's a function, du dx. So 3x squared dx is our g prime. And so we have all right. So we also have our g of x is equal to x cubed plus 1. We look at both of these endpoints. So when x equals 1, so we have g of subtract 1. So x is equal to 0 when x is 1. So that one is 0. And then the second one, when x is negative 1, when x is 1, g of 1, what am I doing? What am I doing? So g of 1. G of 1 is 1 cubed plus 1. 1 plus 1 equals 2. So g of 1 is 2. Then g of negative 1 is negative 1 cubed plus 1. Negative 1 plus 1 equals 0. Those are my bounds of integration. So the first thing I do is change the power of the radical, make it 1/2. So we have 1/2 plus 1 over 1/2 plus 1, which is u 3/2 over 3/2 from 0 to 2, which makes it 2 over 3 u 3/2. We have 2 3/2 minus 0 3/2. So that was 0. 2 3/2. So that's 8 square root of 8 makes it 2 square root of 2. Makes it 4 square root of 2 over 3. So that's the area of that one. Okay. Let's look at example 2. Use the method of transforming the limits of integration. Oh, this is really worked out for us. Okay, let's look at this one. We'll work that one out step by step. Example 2. A. So from pi over 4 to pi over 2, we have cotangent theta plus times cosecant squared theta d theta. Looking at our cheat sheet, which one of these is going to be our u value? Because we have to have a u and we have to have a du. So the derivative of cotangent is the derivative of cotangent theta is negative cosecant squared theta. d theta. So we have u, we need a negative sign. So this one's going to be negative pi over 4 to pi over 2 u du. Because it had to be negative u inside there. So we had to put a negative there, so we factored it out. So let's look at this. So we have cotangent of theta when theta equals pi over 2 and when theta equals pi over 4. So we have cotangent of pi over 2 is cosine pi over 2 over sine pi over 2, makes it 0 over 1, makes it 0. Pi over 4. That's when cotangent pi over 4, which is cosine pi over 4 sine pi over 4 square root of 2 over 2 over square root of 2 over 2 equals 1. So then we have u du. Integrating u, we get 1 plus 1. U squared over 2. So we have cotangent squared of 0 actually that should do it. We have u squared where u is 0, so it's 0 squared minus 1 squared. So it's 0 minus 0 minus 1/2. Negative still out front. So the answer is positive 1/2. Negative pi over 4, pi over 4, cotangent theta, no, tangent theta d theta. Actually, it's tangent x over x. Oh well. First thing I want to look at 4 over pi over 4. Tangent is sine x over cosine x. All right. So if we let u equal cosine x, then du is negative sine x. So it'll be negative. Which makes it the integral of negative integral of du over u and when x is pi over 4, cosine of pi over 4 is square root of 2 over 2. The cosine of negative pi over 4 is 2 square root of 2 over 2 also. So we change the bounds, plug them into u. So we get square root of 2 over 2, square root of 2 over 2. Well, since the bounds are the same, it's a single point, we know the area is going to be 0. But the integral of this one would have been the negative du over u is ln from square root of 2 over 2, square root of 2 over 2 is equal to 0. That wasn't too imaginative of them. All right, now let's look at definite integral of symmetric functions. By symmetric functions, what if we had a half a circle? Or the sine function or cosine function? So the area here is negative, the area here is positive, and if we add them together, we get 0. The area on this side is on the negative side, the area here is on the positive side, add them together, we get 0. So that's the problem we'll be faced with whenever we know we have symmetric equations. Which brings us to theorem 8. Let f, the function f, be continuous. The symmetric interval negative a to a. If f is even, then the integral from negative a to a of f of x dx is equal to 2 times half that integral. Even functions are symmetric about the y-axis. Even functions only have even exponents and may or may not have a constant. term. Those are even functions. So, for example, what that means is this value here is the same value as that one. It's symmetric about the y-axis, get the same y value. So the integral from negative a to a of this function, if I did the whole thing, dx, would give us 0. Because this side here and that side there are opposites. Well, they're opposite signs. So what we can do is, if we only take half of it and double it, then we get the true area. All right. So that's what that's it. That's part A. Part B, if f is an odd function, I won't put it on the same side. I hate to say that, but what's going to be here is to give us twice that distance. Because now we're discussing odd, then the integral from negative a to a of the function is, that one's going to be 0, because odd functions only have odd exponents. So they can be positive or they could be negative. This is negative area and positive area. So for this one, because it becomes 0, we find where, if between negative a and a it equals 0, we find where it crosses the x-axis, the x-intercept, and then we'll change the integrals from the first one and leave the second one alone. So this one, instead of going from negative a to x, would switch to x to negative a. And because that would change the sign of it. So it wouldn't be negative anymore, it'd make it positive. All right, let's look at the example. Negative 2 to 2, x squared minus, no, x to the fourth, minus 4x squared plus 6. Now, since all the exponents are even and has a constant, this is an even function. So that means we only have to do half. Instead of from negative 2 to 2, we go from 0 to 2. This one would be 4 plus 1 over 4 plus 1. X 2 plus 1 over 2 plus 1. 6x. X to the fifth over 5. 4x to the third over 3. 6x from 0 to 2. Since all these have x's, we don't have to worry about that one. So we have 2 to the 5th over 5, 4, 2 to the 3rd over 3, 6 times 2 minus 0. So it's 32 over 5. 2 to the 3rd is 8. 8 times 4. Then now I'll multiply by 2. That's 64 over 5 minus 64 over 3 minus 24 over 1. LCD is 15. Multiply that by 3, by 5, and by 15. 64 times 3, 192. 5 times 64, 320. And 24 times 15 is 240. 24 times 5 is 20. 120. That's a plus. That's a plus. 360. 360 minus 320 is 40, a positive 40. So 40 is 232 over 15. Right, so that's that one. Pretty straightforward. Again, those are taking integrals from a function to an x-axis. Now, let's pretend we have two separate functions. They could both be on the same side, and we have our A and our B, and we look for the area between there. Or from A to B, we're looking for this entire area. So the left bounds of the line x equals A and x equals B, f of x, f of x, g of x, g of x. We same way we've always done it is to find the area between here. We use Riemann sums and break these up into small pieces. So the area itself is base times height. So all of these areas would be, the height would be our functions with the midpoints of each interval. And the base, well, this is the first one, times delta xk. So that's that one. So that finds the area all the way to the bottom. And we take away the second function, g of ck. Take this out of there. What's left is the area between there. So what we're looking for here is this formula. So that's going to be for each little rectangle. Again, and because we have intervals, to make it better, we use this midpoint. We use the midpoint to find the height of it. So to find the area, we got to add up all of these. So we have to add up all of our delta A's from k equals 1 to n, which equals summation of k equals 1 to n of f of x ck minus g of ck times x. Yeah, so it's only the different really we have here is now we have to take the difference of the two functions. This is where f of x is greater than g of x. Because it's the upper minus the lower. Yeah, and we could look at partitions also. So what we're looking at here is the true area, then is the limit of the largest partition as it goes to 0. F of C of k minus G of C of k delta x k sub k. This is the Riemann sum. And what that equals then is our limit from A to B, the endpoints of f of x minus g of x times the delta x. That's what this is what we're looking for. The area between two curves. And the definition of our sheets says this. If f and g are two continuous functions with f of x greater than or equal to g of x, throughout the entire domain, then the area of the region between the curves f and g, y equals f of x and y equals g of x, from the a and b from the lower to the upper points is the integral f of f minus g from A to B. That's what that says. Again, that's on your sheet. So our definition of our integral for areas between two curves is this. Let's look at example 4. Find the area of the region bounded above by the curve y equals 2e negative x plus x below by the curve y equals e to the x over 2 on the left by the line, vertical line x equals 0, and on the right by the vertical line x equals 1. X equals find the area to the region bounded by this function and this function from on the closed interval of 0 to 1. So we know our upper bound. Remember, we're supposed to have f of x is greater than or equal to g of x. Our upper bound is 2e to the negative x plus x. Our lower bound, our lower function, is e to the x over 2 on 0. So the area from 0 to 1 is 2e to the negative x plus x minus e to the x over 2 dx. This is f minus g. So integrating each one of these, the integral of e to the power negative x is eu du. So the derivative of that one is negative, so it's got to be negative 1 x squared over 2 and that one's going to be the derivative. That is 1, so it's e to the x over 2. Yeah, e to the x stays e to the x. All that from 0 to 1. Negative 2e to the negative 1 plus 1 squared over 2 minus e to the 1 over 2 minus negative 2e to the 0 over 1 plus 0 minus e to the 0 over 2. This gives us negative 2 over e plus 1/2 minus e over 2 e to the 0 is 1, so that makes it negative 2. 0 is gone. E to the powers, so it's minus 1/2. So it's negative 2 over e plus 1/2 minus e over 2, distribute that, plus 2 plus 1/2. 1/2 is 1, plus 2 is 3, minus 2 over e, minus e over 2, whatever that equals. Examples we got 7. All right, we're almost there. All right, let's move on to the next one. Example 5. Find the area of the region enclosed by the parabola y equals 2 minus x squared, and the line y equals negative x. Okay, didn't give us any other information. Let's go ahead and graph this function though. First one, 2 minus yx. So minus yx is a downward facing parabola and up 2. Bigger than 1, less than 2, it's just square root of 2. Negative square root of 2. And the line negative x. Actually, so we got to find out where these lines intersect. So this is line 1, line 2. So this is the higher one. That's f of x, and this is going to be g of x because it's higher. So let's set them equal to each other. Let's see where they intersect. So move everything over there. So we have 0 equals x squared minus x minus 2. X minus 2, x plus 1. Set them equal to 0. So we have it, our x-intercepts occur at -1 and 2. That's where they intersect. So this will be our A, and that's our B. So our closed interval will be from -1 to 2. F of x is 2 minus x squared. G of x is negative x. So we're looking for the area. So we got to put a B. F of x minus g of x dx. A is -1, 2. 2 minus x squared minus negative x. So we have negative 1 to 2. 2 minus x squared plus x dx. Okay, so now we could, so we have 2x, x3 over 3 plus x squared over 2 from negative 1 to 2. 2 times 2 minus 2 cubed over 3, 2 squared over 2 minus the bottom one. 2 to the negative 1 minus negative 1 cubed over 3 plus negative 1 squared over 2. Four minus 8/3 plus 4/3 minus 2 plus negative 1 cubed is negative 1, negative 1 is positive over 3. Negative 1 squared is positive 1/2. 4 over 2. 4 over 2 is 2. So that's 6 minus 8/3. Just distribute here. Plus 2 minus 1/3 minus 1/2. 6 plus 2 is 8. Negative 1/3 minus 1 is negative 9/3 minus 1/2. Makes 6. So it's 6 so drop the absolute value. I mean, we have 4 plus 2 is 6. Negative 9/3 makes it 3. So 6 minus 3 plus 1/2. 3 plus 1/2. Six, 7 over 2, I think. Okay. Let me finish that again. That's looking weird. So we have 4 minus 8 over 3 plus 2 plus 2 minus 1/3 minus 1/2. 4 and 4 is 8 minus 9/3 . So 9/3, 8 minus 3. Is 10/2 minus 1/2 equals 9/2. That looks more better. Okay, now this we've done everything else like we normally do, but this time integration with respect to y. So let's look at what it looks like when we do horizontally. All right. So what that means in the past, we've always done it this way with respect to the x-axis. Now we want to do it this way with respect to the y-axis. So now how do we do that? I'm sorry, but there's somebody dropping off a package in my house. Because when we do these integrations, we have to change everything from a function of y equals x to a function of x of y. So for example, our areas will now look like this. Instead of A and B, we're going to go to C and D. We have to change our functions with respect to y now. So look at the example we just had. This is example 7. Y equals radical x. And so says find the area of the region in example 6 by integrating with respect to y. Example 6 is find the area of the region in the first quadrant, it bounded above by square root of x and below by y equals x minus 2. Okay, so let's look at the graph of this one. So the first one, we have when x is 1 and y is 1. 1, 2, 3, 4. When x is 4, y is 2. And so that's the above. That's that one. That's our f of x. Our f of y now. This function, x-intercept is at -2 up to over 1. No, slope is 1. So up 1 over 1, up 1 over 1. Nope. Yeah, I gotta make it more accurate. So So they'll intersect here at 4, 2. We want to know this whole area here. So we're going to get, these are our delta y's. We have to solve, so we have to square both sides. So x is equal to y squared. And the second one, y equals x minus 2. X equals y plus 2. Now, since we're going horizontally with respect to y, this is our outer equation. So this equation is our f of y, and this is our g of y. We have to find out which one's on top, which one's on the bottom. Where they intersect, set them equal to each other. So 0 equals y squared minus y minus 2, y minus 2, y plus 1. Negative 1. But since negative 1 is not in our range, we can't use it. So we'll have from 2 to 0. That's all we're looking for right here. Since we factor these out, we can't use negative 1. We only want in the first quadrant. Okay, so our bounds are going to be from 0 to 2. Those are the y values. Let's see where they're going to go. I mean, what values we have. 0. Well, this one's got to be at 0. And when we square 2, we get 4. So our bounds of integration are going to be from 0 to 4. That's I'm doing y, I'm sorry. So our bounds of integration are going to be, this is C and that's D. So the area is going to be from C to D, f of y minus g of y, dy. From 0 to 2, our f function was x or y plus 2 minus our g function, which is y squared. So we have y squared over 2 plus 2y, y cubed over 3 from 0 to 2. Since they all have a value of y at 0, I don't have to worry about that one. So just, I'm only interested in 2 squared over 2, 2 times 2, 2 cubed over 3. All those are 0. 4 over 2 plus 4 minus 8 over 3 6/1 minus 8/3 was 18/3. Is 10/3. So that's the area of that one. All right, that's it for chapter 5. So next time we'll start chapter 6. All right, any questions? If not, then I'll see you guys on Thursday. Remember, Mardi Gras today and tomorrow's Ash Wednesday or the beginning of Lent. Whatever, how you want to look at it. All right, everybody. Good luck and have fun. Be safe.